Good morning. Today let's look at the double sideband suppressed carrier, which is the most fundamental type of amplitude modulation. So if you remember in the last lecture, we had the modulating signal, which could be our voice, for example, any real world signal with low frequency, and then we have our carrier signal, which is a high frequency signal. If you simply multiply the modulating signal with the carrier signal, our product is this, the AM signal. So our amplitude modulated signal. And this is the signal that we send through the antenna. So we can send this wirelessly through our antenna. Now, this type of amplitude modulation where we simply multiply it, so here we multiply, this is known as the double sideband, should be suppressed carrier. So all double sideband suppressed carrier is just a multiplication between the modulating signal, say our voice, multiplied by the carrier signal, which is a high frequency signal that we choose the frequency of, and our output is the amplitude modulating signal, which is the double sideband suppressed carrier. So in this lecture, let's look more deeply into the double sideband suppressed carrier, its bandwidth, its power calculations, and the pros and cons of using double sideband suppressed carrier. Let's go. Okay, so first you want to express both the modulating signal and the carrier signal mathematically. That allows us to do calculations that get us to the AM signal. So for the modulating signal, that can simply be expressed as mt. So m is the modulating signal, t is time of course, and that equals am. So am is the amplitude of the modulating signal multiplied by cosine 2 pi fm. So fm is the frequency of the modulating signal multiplied by time. So that is frequency of modulating signal. And that is the amplitude. And so that is simply how we can express our modulating signal. Now in this simple modulating signal here, we can see that the amplitude is 1. So we can just place 1 over there. And we can see in our frequency, I've already done the calculations, but it's 1 kilohertz. Well, it should be a little k, 1 kilohertz. And that 1 kilohertz goes in there. Now, similarly for the carrier signal, we can just say C of t, so that is carrier signal in time, equals AC. So AC is the amplitude of the carrier signal, multiplied by cosine 2 pi fc. Fc is the frequency of the carrier signal, multiplied by time. And simply put, that's how you can express the carrier signal and the modulating signal mathematically. So I'm going to rub all this out, and then we'll do the calculations. Okay, so before we jump into calculating the bandwidth of the AM signal, let's look at what the bandwidth is, just to jog your memory here. So bandwidth is simply the range of frequencies present in your signal. So for example, if signal A has frequencies from 10 Hz to 20 Hz, then its bandwidth is simply just the range of frequencies, which is from 10 Hz to 20 Hz. This can be calculated as bandwidth equals F max, so the maximum frequency present, minus the smallest frequency present. That's the bandwidth. So for signal A, that would be 20 Hz. 20 Hz is the max frequency, minus 10 Hz. So the bandwidth is just 10 Hz. So we have that's our range of frequencies. Okay, let's calculate the bandwidth of the AM signal, or the double sideband suppressed carrier. Okay, so to get the bandwidth of the AM signal, we just need to find the range of frequencies present in the AM signal. So to do that, let's start with the calculation. So our equation for the double sideband suppressed carrier, which is ST, the AM signal, is AM AC cosine 2 pi f fmt cosine 2 pi fct. And so now to find the range of frequencies, we just do the multiplication. So that's multiplication. So st equals am ac divided by 2 cosine 2 pi fc plus fm t plus am ac divided by 2 cosine, that is 2 pi fc minus fmt. As you can already see that we have this fc plus fm term and we have this fc minus fm term. So we'll use these to find our range of frequencies and hence the bandwidth. So if you remember, our bandwidth equals the f max minus the f min. So naturally we can see that adding the two frequencies together will give us our f max, and subtracting the two frequencies will give us our f min, or our minimum frequency. So that means the bandwidth equals to fc plus fm, so that's our maximum frequency, minus the minimum frequency, which is fc minus fm. And so now by just simply solving this, so we can do fc minus fc, which is fc goes, and now we just have fm minus fm, which just equals to 2fm. So our bandwidth equals to 2 multiplied by the frequency, the modulating frequency, and that is the bandwidth of the double sideband suppressed carrier. Okay, so let's draw this on a graph, a frequency amplitude graph. So frequency on the x-axis, and on the y-axis we have the amplitude. So let's try to plot what the double sideband suppressed carrier looks like. So in the middle we would have our carrier. Just for reference, we put our carrier, so that's the frequency of the carrier, and that is 1 megahertz. Now if you remember from the last slide, our frequencies were this: fc minus fm, and then fc plus fm. So let's graph fc minus fm and fc plus fm. So that would be our fc plus fm. And then over here we would have our fc minus fm. So as you can see, we've only got two terms, fc minus fm and fc plus fm. We don't actually have fc alone. That means that the carrier does not exist in the double sideband suppressed carrier signal. So this AM signal does not have a carrier signal inside because there's no fc term alone. There's only fc minus fm and fc plus fm. So as a matter of fact, this carrier doesn't actually exist. It doesn't do anything. It's not there. It's not present in our signal. The frequency of the carrier is not present in this AM signal. So that's why it's called suppressed carrier, because there's no fc term alone. It's only fc minus fm or fc plus fm. So there's no carrier alone. That's why it's called suppressed carrier. So no carrier. Now you can see these two terms here. We have fc minus fm and fc plus fm. These are called sidebands. So these two are known as sidebands. And as you can see, we have two sidebands. One sideband is, so sideband 1 is fc minus fm, and sideband 2 is fc plus fm. And because we got two sidebands, that's why we have this word double sideband. So double sideband, and then suppressed carrier because the carrier does not exist. And that's where the term double sideband suppressed carrier comes from, or if we shorten it to DSB-SC. So I will commonly shorten it to this. So as you can tell, and you might be asking yourself a question, doesn't that mean we're duplicating data? Yes, you're right. So in DSB-SC, which is just simply the shorthand for double sideband suppressed carrier, we are duplicating our signal. Okay, so now let's calculate the power of the AM signal. So just as a quick reminder, the power equals VRMS, so voltage RMS squared, divided by resistance R. So that's just voltage RMS, and in our case is just the amplitude's RMS, and R is resistance of the internal circuitry, and then P is just our power. So how much power of the signal are we actually transmitting? What's the transmission power? So to calculate this, remember that our voltage is just basically our amplitudes of the signals. So our amplitudes are AM and AC. So that's the amplitude of the modulating signal and amplitude of the carrier signal. Now, those aren't actually RMS. These are max values. These are max values. So instead, we want to convert these to RMS. And so to convert these two to RMS, AM and AC to RMS, we simply divide by root 2. So divide by root 2. Okay, so now these two values are suitable to use as voltages in this equation. So now let's rub stuff out. Okay, now so each sideband has the AM value and the AC value. So to calculate the power, we are basically saying, so divided by resistance, that is AM, amplitude of the modulating signal, divided by root 2, multiplied by AC, divided by root 2, and this entire term is squared. So that equals AM, AC, 2 root 2 squared divided by R. And that can be simplified into AM squared and AC squared divided by 8R. Now, this is not the total power of the entire double sideband suppressed carrier. This is just a single sideband power. So single sideband power. And so if you want to find the total power required for the entire double sideband suppressed carrier, you actually just need to multiply this by 2. So if I rub some more stuff out, rub all this top part, our total power, which you can say is PT, is just equal to AM squared, AC squared, divided by 8R, multiplied by 2, because remember we have two sidebands, which just equals AM squared, AC squared divided by 4R. And that is the total power transmitted when using double sideband suppressed carrier. Of course, we don't know our R, so we just leave that as an unknown variable. Okay, let's look at the pros and cons of the double sideband suppressed carriers. So the main pro is we do not send the carrier signal. So we do not the carrier signal. And this is a pro because we save power. If you're wasting your power on random stuff like the carrier signal, remember the carrier signal holds no information. So remember, carrier signal, no information. So because we don't send the carrier signal, because the FC term does not exist, we are saving a lot of power. In other types of amplitude modulation, we actually send the carrier signal, so we waste a lot of power on just the carrier signal, and the carrier signal carries no information, so it's useless. So the fact that double sideband suppressed carrier does not send the carrier signal, that means we save a lot of power. Now, another pro of it is that it's easy to generate. Remember, to generate it, all we do is modulating signal multiplied by the carrier signal, and that's it. Simple circuitry, easy to understand, easy to implement, no big problems there. Okay, now let's look at the cons of the double sideband suppressed carrier. So cons. So the main one being we duplicate information. So duplicate information. Remember that we have FC minus FM and FC plus FM. They are both the same data sent, the same signal is sent, or same information is sent, just at a different frequency band. So duplicate information means we actually waste power on that. We waste power on duplicate information. And so you actually need, well, if you remember the bandwidth, we actually need 2 times the modulating frequency. So if you look at it like this, that means we need double the bandwidth to send the same data. So that's redundant, is essentially redundant. It's double the bandwidth required for half of the data, half the signal. So because you have FC minus FM and FC plus FM, the bandwidth is doubled. And if you're in an area where you have limited bandwidth, so you can only use certain frequency bands, where this type of double sideband suppressed carrier, it just uses too much bandwidth. So that is too much bandwidth. And if you can't afford to use too much bandwidth, then double sideband suppressed carrier is going to cause you problems because it requires double the bandwidth. Okay, so let me rub this out. So duplicate information means double bandwidth. And majority of the times we are actually limited in bandwidth. So double bandwidth is no good. Okay, so another problem is you actually use more power because you have to use power for both sidebands. So double power. Because remember, you need power to give to FC minus FM band and FC plus FM. They both require equal amounts of power just for duplicate information. So you're spending more power just for the same information to be sent through the antenna. So we are doubling the power, and majority of the times we are both limited in bandwidth, and if you have a little microcontroller or a little tiny like a car or something, you're already limited in power to begin with, so you can't be doubling the power just to send the same information. So double bandwidth and double power is a huge problem with double sideband suppressed carriers. Okay, and another problem with double sideband suppressed carrier is it's actually got a very complex circuit to demodulate the signal. So remember, we send the signal to the antenna, our modulated signal to the antenna. Now someone has got to receive that double sideband suppressed carrier signal, and they got to demodulate it, and the circuit required for that is quite complex. So quite complex demodulating circuit. Okay, so they are the main problems with double sideband suppressed carrier. Okay, so in this video we have looked at double sideband suppressed carrier, its equations, finding the bandwidth, its frequency graph, the power, and then we also looked at the pros and cons of the double sideband suppressed carrier. I really hope you enjoyed this video. Please stay safe, and I'll see you next time. Thank you.